Hello all of you. So in the last lecture we have been discussing the molecular dynamics simulation method, and finally we have been discussing the interaction forces and energy between the system. So today I will take the discussion further and discuss first the interaction energies in more detail, and then finally we will come to the Monte Carlo simulation. Before I go further, I want to emphasize that the interaction energy and forces that we have discussed, the same idea applies also in the Monte Carlo simulation method, because this is what represents the system, right? So the interaction energy part of the discussion is not really particular to the molecular dynamics simulations. So I was telling you that ultimately it comes down to finding the interaction between the particles, the u of r. If I know the mathematical form of that, for one component system, this is what we are interested in. If we have a multi-component system, we can find u alpha beta r, where alpha and beta refer to species, right? So let's say if I'm looking at a solvent solute system like a solution, you will have something like u between the solvent and solute, similar to epsilon ps in the lattice model, u between the solutes, similar to the epsilon pp in the lattice model, and u between the solvents, that is similar to epsilon ss in the lattice model. But this is much more general, because now I am accounting for the all possible variations in the separation. In the lattice model, we assumed that the separation is fixed, so as to speak, because the interactions only occur between the neighboring particle, right? So that's only, I would say, a poor limiting case or of the more general scenario, because for most interactions, it is not applying only to the neighboring molecules or neighboring particles, and secondly, the particles are not going to be constrained at that particular location. So by doing that, we have really moved off lattice, so as to speak. By off lattice, I mean that now I am doing in a continuous kind of a space. So what will that interaction look like? So there are two ways to think about it. The first way to think in, like, I would say, a more physics oriented way of what are the possible forces that may possibly exist and what those forces will give in the form of u of r. The second way is to look at the chemistry in more detail and try to figure out what will be the energy between, say, a particular species, say ethanol and water. Then we are worried about the chemistry of it. And of course, that also has to come from the fundamental forces of physics, but then we are also considering putting the chemistry into consideration and trying to find which chemistry will give rise to which kind of forces, right? So these two ways I will classify as some sort of a generic representation versus kind of a molecular representation. The latter is typically referred as force field. So if I am including chemistry, that means you give me a compound and I need to have some mechanism to tell you what are the forces between them or what is the energy between them. That is what the force field does, right? In the generic case, I am only telling you what will happen if the interactions are, say, Coulombic, or the interactions are, say, of the nature of van der Waals, without any regard to a particular system under consideration. So all the systems which are Coulombic or ionic will show that kind of a behavior. So clearly the generic kind of an approach will not give you accurate predictions when it comes to comparison with experiments, but the force field approach, where I am including the chemistry, will give you the prediction that is more accurate quantitatively. Nonetheless, the qualitative picture is captured here as well. So I can say the first approach captures the qualitative picture and the second approach captures both qualitative and quantitative picture. So let's look at the generic approach to begin with. So we know, for example, that if you have if the Coulombic interactions are present in the system and we are considering like charged species. So, one component system, all the species have to be having the same charge. In that case, there has to be a repulsion between them, and the repulsion will give rise to a positive energy. So, Coulombic energy is represented as something like Q alpha. So, in general, for U alpha beta, I can write Q alpha beta, Q alpha Q beta divided by 4 pi epsilon naught epsilon multiplied with R. So, it goes like 1 by R. So, it will look like something like this for the like charge species, right. So, since I also want to consider the case when they are unlike charged, let me put that as something like U alpha beta R, that is I am considering a multi-component system. So, for unlike charge, clearly this is going to be negative. So, one of them will have positive charge and one of them will have negative charge, and in that case we will have attraction between them. So, this is a repulsion and this is an attraction. So, I have only showing the shape here. Of course, the magnitude of that will going to change as the charges change, right. But for the sake of like the mathematical form of it, this is what it will look like. Next, or I would say even before what we have been discussed, we can consider an ideal gas. So, ideal gas would be what? Ideal gas is when there is no interaction, right. So, it will follow along this line where irrespective of separation, there is no interaction whatsoever between the two particles in the system. Then we can consider a van der Waals gas or van der Waals model, and I was telling you that only difference between the van der Waals and the ideal gas model is we do not allow the particles to overlap, or we are assuming that the particles have a finite size. So, that really limits, I would say, in an ideal gas this can happen, but in a van der Waals gas all that could happen is something like this. They can come in close contact, but they cannot really overlap, right. But beyond that, as long as they are not contacting, there is no interaction whatsoever, right. So, what will that look like? So, since the overlap is restricted, what this means is, let us say if I represent some R O as the overlap distance, then for the values less than this R O, this is going to be like infinite, right. So, it will be like pretty much like this. And why is that? This is so because once the interactions energy becomes infinity, the particles will not overlap, because ultimately the system wants to go towards lower energy state. So, a positive energy and a positive high energy is something that the system will not like to have. So, as soon as we are less than R naught, R O, the energy goes to infinity. So, I can say for the van der Waals model, for the van der Waals gas, by the way, the model itself is called a hard sphere model. That is to say that we assume that there is a hard core, so as to speak. So, hard core is the word that is more common in molecular simulation literature. For this particular model, the U of R has the form infinity when R is less than R naught, that is whatever the overlap distance is when the close contact distance is, and 0 otherwise. right. So, this becomes my hard core model, and of course, beyond this point it is going to be following the ideal gas like behavior. Now, there is a problem in this particular function, and the problem is, let us say if I am using it for molecular dynamics, I have said that the force is given as the gradient of this u, and u is the sum over this small u between every pair of particles. So, since I have to find a gradient, what this demands is that capital U has to be a, this is by the way small u, keep in mind, that is between the particles. This capital U, this guy, that is total energy of a system, that has to be a smooth function without any discontinuities. Whenever there is a discontinuity, then the gradient is not defined. So, therefore, what it means that I cannot simulate using MD, because in MD we need to find forces, and since the function is discontinuous, we cannot find the gradient, and therefore, the forces cannot be evaluated, and therefore, we cannot do MD. We later on will show that we can still do a Monte Carlo simulation, because it approaches the problem a bit differently in terms of energies as opposed to forces, but at least MD cannot be done. So, instead of that, I mean, what difference will it make in terms of the qualitative behavior if I represent a function that is very close to the hard core, but is not discontinuous, that is a smooth function. So, I will draw a function that will look like something like this, for example, right. So, instead of like having a discontinuity at R naught, it is kind of like going smoothly to 0, and this is still a very small distance. What this means physically is that it is not that I do not allow overlap, but as soon as the overlap starts to happen, I will have a strong energetic penalty, right, as opposed to saying that you are either having 0 interaction or infinite interaction when they come in contact. We can say that it is going from 0 to infinity or very large value a bit slowly than having a discontinuous jump. This is what is referred as a soft core interaction. That is still repulsive, but since it is a continuous function, we can use MD for that. There are small subtle differences in the behavior for these cases, but qualitatively there is not too much change in the behavior going from hard core to the soft core model. That is why we typically prefer soft core model. I will not discuss the form of the potential right here, but keep in mind that this is what the functions would look like. Now, in reality, there can also be some other interaction apart from the overlap thing that we have discussed. In general, let us say if I am considering a liquid or even for many gases, you can have some attraction between the particles at short distances, right. So, you may have some short range interactions, let us say water molecules. So, water interacts with nearby water molecule with a hydrogen bond. Hydrogen bond is not as strong as a Coulomb interaction, but nonetheless it is there. This gives rise to a negative energy, so as to speak, and that has to be considered, and the fact that both the magnitude is small and the range is small, both has to be taken care of, right. So, in general, one of the most common potential is what is known as a Lennard-Jones potential, and I will discuss that later in the course. There are other potentials that also achieve the same thing, that is called a Morse potential, and we are simply discussing the mathematical forms right now. Why I am using one, why I am not using one is something that we can take on a case to case basis. So, that potential I can represent whether it is a Lennard-Jones, that is called LJ in literature. Or Moore's. They have slightly different mathematical forms, but one thing that is common in both of them is they still have no overlap. The particles cannot overlap, but they have some short range attraction, just like water molecules. Two water molecules cannot overlap, but at shorter distances they can form hydrogen bonding, right. So, therefore, it starts from almost close to infinity at very small values of r, then goes negative. By negative, it means that there is some attraction, and this depth of this kind of a well represents the strength of the interaction, and this broadness of the plot represents the range of the interaction, right. And using various potentials, we can control both of them. So, if I know what is the range in which the interactions are active or interactions have significantly large value, then using that information, I can construct some kind of a potential that captures this particular behavior. So, this is an example of the generic kind of models we can build, and this is already good enough, because if I start thinking from the lattice model that was starting, there we simply had one parameter epsilon, and there was no control on how the interactions are varying with distance. That has been taken care of here, and qualitatively it is not very difficult to figure out which kind of interactions are active in a system. At a qualitative level, we can see if the molecules are charged or the atoms in the molecules are charged, then there can be a Coulomb interaction between them. In fact, it turns out that Coulomb can be present even within neutral molecules. I will come back to that point later. But if they are charged, then clearly there is Coulomb interactions. We can expect a van der Waals interaction to be present for most liquids. There can be short range attraction that I can represent using Lennard-Jones or Moore's potential or some other potential. And if it is, I want to study the behavior in the ideal gas limit or for the gases, we can go for a soft core if I want to do MD simulation, right. And this will already give me the behavior for a large variety of systems, still not considering the I would say the chemistry in any kind of a detail, but considering all possible kinds of behavior that one can obtain. That is why I said it is more physics oriented, so as to speak. So, this is very much possible. Now, let us come to the business of the force fields. Let us say if I am thinking of a force field, what will that entail? The force field should also capture the qualitative behavior that I have described here, but there can be a complex combination of various kinds of interactions. For example, there can be electrostatic interactions between some part of the molecule with some other parts of other molecule. There can be van der Waals interactions between some part of molecule with some part of molecule. There can be behavior akin to a soft core. There can be a behavior akin to a pure Coulomb interaction. All these possibilities can happen. So, a force field is actually constructed as a complex combination of these things, combination of various mathematical forms. Now, how will I get that mathematical form? There are two ways to get that. First of all, I can again do experiments. I can assume some mathematical form of force field. I do some kind of fitting, just like I was telling you for the chi. In a similar way, I can fit the parameters of the force field and I can get the force field for the system, right. It turns out that most of us don't have to do it. Most of us working in the application of the molecular dynamics or Monte Carlo simulation can benefit from the force field development efforts that has already happened since like last 20-30 years. In fact, there was a Nobel Prize coming from a group who has developed a force field. So this has been there are force fields of various names, and I will come back to that when I discuss the molecular dynamics, who are doing this fitting exercise, and they will tell you that for these kind of molecules, with those kind of molecules, use this kind of force field. So there are prescriptions. So in some sense, the force fields are still empirical if we are doing some kind of fitting exercise. So why do I have to do a fitting? Is the question that we can try to answer, right? So if I think of like actually at a molecular level, the forces between the molecules, we really have to think that every molecule is some sort of an electron cloud. If I really zoom in and are able to see the molecules, let's say even two water molecules, we are in fact dealing with interaction between two electron clouds there. So if I really want to find the interaction between these two electron clouds, what I should do is I should solve the Schrodinger equation, because the whole idea of considering the interaction at the level of electrons and protons and so on, that comes in the regime of Schrodinger equation, right? So ideally we should solve Schrodinger equation, find the interactions and feed that into molecular dynamics. In fact, that is exactly what is done in what is known as ab initio method, ab initio molecular dynamics method. Now it is not very difficult to imagine that that is going to be a very complicated exercise. So I want to simulate a relatively large thermodynamic system. The Schrodinger equation is already complicated even for very simple molecules, right? So the whole quantum chemistry as of now can only work for very small systems, right? So if I want to take that approach to like slightly microscopic system or systems containing large number of molecules, then it is going to be a very cost consuming affair. And therefore, even though the ab initio methods are in principle the correct way of doing it, they are not typically employed in molecular dynamics. Instead, what people do is they develop these force fields, and force fields are developed earlier mostly using experimental data, but now they are also using some small quantum chemistry simulations for smaller systems and using that to parameterize or to fit the force field equations, right? So these can be done, and these will then include the effect of the chemistry of the molecules. It just turns out that it is mathematically more involved and therefore numerically more involved than compared to the generic method that I have been discussing, right? So if you go back to the literature, the generic methods are the ones that have been used, I would say, a lot in the initial era of computers. The molecular methods, starting from a force field, even if it is empirical force field, have come a bit later, and right now we are at a stage where we can do, at least for small systems, ab initio simulations, right? So keep in mind that whenever we say that we are using an empirical force field or we are using a generic model, we are still not in a fully predictive kind of a method. The method is not really first principle. When I am doing quantum mechanics, the method is a first principle method. You give me a chemistry, I will give you the behavior. In molecular simulation, the method is not completely first principle because the force fields are trained using experimental data. If they have been trained using quantum mechanics simulation data, then we can still say as first principle that approach is coming up now. But if we are using experiments to train the force field, it is not completely a first principle method. Nonetheless, it turns out that once I have the force field under given conditions, that really works pretty well for a variety of conditions. Let us say if I now vary temperature or I vary the composition, the force field have been shown to be efficient in a multiple of the scenarios, right. So, it is just that there is now a transition from getting the generic behavior to an emphasis more on including the detailed chemistry, and the molecular approaches aim to do just that. So, I want to complete the discussion here. What we will see in the next few lectures is that I can use the same interaction potentials in what is known as the Monte Carlo simulation. That really is a very attractive alternate way of doing MD. First of all, as I already hinted, I can, for example, do hardcore interactions, but that is not the key idea or the key benefit of the molecular the Monte Carlo simulation. The key benefit is it tells me a better way to sample the phase space, right? Because if you recall, I started with saying that the molecular dynamics is starting from one state point and doing the trajectory for a limited time. So, in a sense, we are looking at only a small portion of the large phase space, and Monte Carlo gives me a better way to sample the phase space. But the key idea that we will borrow from the discussion that we have already done is that the Hamiltonian is not going to change, the description of the phase space is not going to change, the interaction potentials or the U of R are not going to change. The fact that we can do a generic simulation or a molecular simulation using force field, that is not going to change. What will change, however, is how exactly the simulation is being conducted, how exactly are we moving within the phase space. And in the molecular dynamics simulations, we have used the Newton's laws of motion to evolve the system, and in Monte Carlo you will see it is based on a completely different idea, but still gives the same equilibrium behavior as the molecular dynamics simulations. So, with that I want to conclude here. Thank you.